Let's look at the balance of plant basics. So balance of plant wise, this is just a process flow chart, a very basic as you can get process flow chart for a 1 megawatt electrolyzer. So the numbers here are given for 1 megawatt of electrolysis, and you can, if you have 2 megawatt, just multiply the numbers by 2, etc. So typically, what we'll have is we'll have a water inlet into the water purification system. And this is going to be tap water. In the UK, typically tap water is about 600 microsiemen per centimeter. And this tap water will go into the water purification system. And there will be, and we'll go into how this works. For now, it's just a box. By the way, if we will go into the water purification system shortly, but at the moment, all we need to know is out of this 325 liters, about 125 liters will be drained through the reverse osmosis system, and about 200 liters will go into the oxygen water separation vessel, and this is going to be used as process water for the PEM electrolyzer stack. So the water coming in, like we said, is going to be about 600 microsiemen per centimeter, depending on where the world you are, and it could be less, it could be more, and the water going into the oxygen water separation vessel. So the water coming out of the water purification system, what you're looking for is, let's say around 0.1, 0.2 microsiemen per centimeter, but we'll go into that shortly as well. And then from here, we've got the oxygen water separation vessel. It's going to be it's going to be a tank filled with water, and oxygen will be on the top. And what we do here is we have a main circulation pump which pumps the water through the electrolyzer stack. So it pumps it in and the water comes out on the other side, and then later on it will go into the plate heat exchanger. And the plate heat exchanger is going to cool down our water. It will provide cooling, but the plate heat exchanger is going to be inside, because we don't want the water to go outside, because in the winter it's going to freeze. So we will have a different medium, which is going to be some sort of a coolant with an inhibitor inside, which will go outside into the air blast cooler to provide the cooling. And what we also have is this purified water as we are electrolyzing. And by the way, when we're electrolyzing at relatively low current density, there'll be quite a lot of certain impurities will be released into the water, and we must purify that. We must take that out. Otherwise, eventually, the conductivity will keep on peaking up, and we'll get to a point where it's too high, and we must stop the electrolysis, because if we run the electrolyzer with crappy water, then the stack will basically, and we'll go into how that works a little bit later, but essentially the stack will not have a very long life if we run the stack with terrible water. So what we do is we have a water repolishing pump, and there'll be a water repolishing loop which will pump about 50 liters a minute back into here, and there'll be an extra sort of 50 liters per minute loop here, which, by the way, the 50 liters per minute comes from, so you take approximately 1 to 5% of the amount that you're circulating through your stack every minute. You are going to also repolish in the repolishing loop. It can work this way, or it can work in a slightly different way. You have a completely different water repolishing system, which is completely separate from the water purification system. So you pump it into a separate water purification system, and you have a loop to make sure that you are repolishing the water that's in here in order to rid of those chemicals that we've introduced into it. So let's talk about the right-hand side here. So this is pretty obvious. We've got the power supply, DC power, positive, negative, 1 megawatt, and on the stack, we've got the hydrogen line coming out on the bottom here, and typically it does come out on the bottom because you want the water also to drain out on the bottom. You don't want a lot of water in the hydrogen side of the stack to linger. So you will have the hydrogen and the water coming down on this line, but we need to get rid of that water. So the water is heavier. The water will stay on the bottom of this vessel, and the hydrogen will bubble up to the top. It will come up to the top. And the hydrogen, which is still really saturated with water, will go into this part, which we'll come to in a second. But what we also have is there is going to be another loop which goes back to reuse this water, because remember, we've just put in all this effort to purify this water, and this is still relatively good water. This is going to be about 5 or maybe 7 or maybe sometimes even 10 microsiemen per centimeter. We want to reuse this water. We want to just repolish it just a little bit. We want to reuse this water. We do not want to get rid of this water at all. So what we do is we allow this water to go back into the water purification system. It will be re-polished, and it will be sent back into the oxygen water separation vessel for another go. And we must have some way in order to vent out the hydrogen that is going back into the water purification system, because the water purification system will have air in it, it will have oxygen in it. We must make sure that we are not putting this any amount of hydrogen back into the water purification system. So we need a vent system, because this hydrogen water separation vessel is going to be at 30 bar, right? Because the system pressure, the typical system pressure is about 30 bars. So this is on the hydrogen side. This will be at 30 bars. So when you depressurize this water, there'll be hydrogen bubbles coming out all over the place, and you want that to happen here in your hydrogen vent, not in here in your water purification system. And then finally we come up to this thing on the right-hand side, which we've got the deoxidizer. And you should remember, the hydrogen that's coming out on the top, it won't have any liquid water in it, but it will be very highly saturated with water, but it won't be liquid water. It will be, we have to take that water out. So what we do here is we have a deoxidizer, which, yeah, you kind of guessed it. It takes out the oxygen. It deoxidizes it. So it takes out the oxygen, the remaining oxygen that we have in the hydrogen. Essentially, it's a reactor. It's a palladium-based catalyst that is in this vessel, and it takes the oxygen, mixes it, reacts it with the hydrogen, and we'll have a little bit of extra water, which we don't want to condensate here, by the way. So that for that reason, it has a little bit of positive heat here. There's a small heater for this vessel typically, because we don't want any condensation to take place in here. And then downstream of that, we've got the temperature swing desiccant dryers, and we'll go into how that works later as well. And then downstream of that, we've got purity monitoring, and then that amazing, really great, very, very pure hydrogen is then going to our client. So let's jump into the different subsystems in our PEM electrolyzer. So we've got our water purification system. So this water purification system on the left-hand side, you can see, in fact, let's go through these first. So we've got the carbon and particulate filters, we've got the water softening unit, we've got the reverse osmosis. So at this point, at the reverse osmosis point, so the water going into the reverse osmosis is going to be sort of about 600 microsiemen per centimeter. Downstream of the reverse osmosis filter, however, we will get to around 10, 15, sometimes 20 microsiemen per centimeter in a really good reverse osmosis filter, or reverse osmosis membrane. And downstream of that, we are going to have a mixed bed DI resin. There could be a different option for that as well, which we'll come to in a sec. But essentially, that is how it works. So you've got on the left-hand side, you've got your mixed bed DI resin, you've got the water softening, you've got the reverse osmosis. We also have, and this kind of comes under the innovation It's kind of an innovation, but kind of not, because already a lot of OEMs are offering an option for what I'm about to talk about, which is, of course, electrodeionization. I nearly fell over there. Electrodeionization system. So on the right-hand side, this is the old way of how most electrolyzer OEMs used to polish their water, which is using the mixed bed DI resin, this is what it looks like. It's nasty stuff. In fact, yeah, he's touching it with his hands. I would definitely not do that. I did that once, and by the time I got back to the hotel, my hand was very dry and very, yeah, it's nasty stuff to touch. But essentially, every few months, you have to go on site, take the top off, shake it out, and replace it with new mixed bed resin. And that's something that we don't want to do. So we've got something amazing here. We've got the electrodeionization. So electrodeionization, this unit, it doesn't need any maintenance. You don't need to replace essentially the catalyst. You don't need to replace that every 2, 3, 5 or 6 months. You just run it. It works on DC power. You just run it, and there's virtually no maintenance that you have to do on it. You could say that, okay, but you could have mixed bed DI resin which regenerates itself. However, I've never seen that used in an electrolyzer. I don't think anybody has has ever regenerated the mixed bed DI resin. You could, but it's just so cheap to replace it anyway that most OEMs have replaced it. And it's very, very important. We don't want to. It's very, very important that the water is very, very, very good quality. Some people refer to it as sexy water. It has to be really, really good, high quality water. Actually, the water, after it's in contact with this catalyst, so out of these vessels, the water that comes out of these vessels is at around 0.1, sometimes even 0.09 microsiemen per, sometimes even 0.09 microsiemen per centimeter, and the theoretical lowest that you can get to is 0.056 microsiemen per centimeter. So you're actually able to get to a very, very close to the theoretical minimum conductivity of water. So, and this kind of comes also under innovations, but I haven't put this under innovations because some OEMs are already offering this. So, and what we're talking about here is the water purification system pressure. So some systems, it's atmospheric pressure, but other systems, it is low pressure. So it won't be high pressure, but it will be an ever so slight pressure, up to 2 or 3 bars. And what it does for us is it allows us to, it prevents ingress of impurities. So it's just like when you cut yourself, the blood will come out, but nothing will go in. And you don't want anything to go in because you just will put all this effort into purifying that water, and you don't want to scuttle that. Improved water recirculation with slight positive pressure. So obviously we're talking about the water purification system, put an ever so slight pressure on here, we are going to look at the stack anode chamber inlet versus outlet connection. So I've got a little prop here. So the water that goes in is going to be 100% of the water that goes in. I'm not going to fill it up too much here because I'm going to have to drink this as part of my prop. So just imagine this is 100% full. So we put in this water. It's all 100% water. And this is what this part shows here. It's 100% water, right? Now, about 99.8% of that water is used to cool down the stack membrane surface. Because we've got the stack membrane surface, there's a lot of inefficiencies that take place. Of course, electrolysis is not 100% efficient, so we need to remove that heat. So 99.8% of the water is there just to remove heat. So I'll show you how much. 99.8%, not to scale. I must say that because I'm in Germany. I have to be very precise. It's not to scale. So 99.8% of that water was actually used just for cooling. And 0.2% of this water, about this much water, 0.2%, is used for hydrogen and oxygen, splitting it into hydrogen and oxygen. Now, the hydrogen will go over to this side, and let's just pretend about, and it's completely, again, not to scale. Let's say half of this 0.2% turns into hydrogen, and the other half of that 0.2% turns into oxygen, and it doesn't, but let's just assume that for a second. You will have your oxygen on this side and your hydrogen on this side, and we're only talking about the hydrogen here. So this graph is only about the hydrogen. So 100% of the water comes in, and so just bear with me here for a sec. So 100% of the water comes in, 99.8% of the water goes out that went in. 0.2% is used to convert into hydrogen and oxygen. Well, here's the thing though. Let's just say 0.1 is oxygen, 0.1 is hydrogen. That 0.1% of oxygen, of the water, once we split it and turn it into hydrogen and oxygen, just the oxygen part is going to be 38% extra. We'll add 38% extra volume compared to the water that we had going in. So where does this come in? Well, guess what? When we have, I'm going to put this down because otherwise I'll split it. So when we have the water coming in and the water is going out and there's no electrolysis, we might achieve 1,200 liters per minute with our pump. However, when we start to electrolyze, we're introducing extra 38% of volume here. So what we have, the volume we have going out is going to be 38% more because of all the oxygen that we've added. So the outlet pipe has to be larger, but also if at 0% output we achieve 1,200 liters per minute, when we ramp up to 100% output, that water flow is going to come down a little bit. So we must make sure that our stack is designed in a way that it allows easy flow for the water. And of course, we must make sure that the stack pump, when we size the stack pump, it takes into account that it's not just water going in and water coming out. No, it's an extra shed loads of oxygen coming out as well, which will not only mean that there'll be a higher volume, but it will also mean that it's not going to be laminar flow, it's going to be turbulent flow because you have all this gas in there as well, all this oxygen. So let's jump onto the next slide here. And the electrolyzer stack membrane, and we kind of talked about this earlier, it allows water crossover. So it allows the water to go from the anode chamber over to the cathode chamber, and we'll go into how that works shortly. But and you know, this is just kind of summing it up. So we've got the hydrogen systems. This is the hydrogen system. The hydrogen system is going to be at 30 bars. Of course, the stack on the hydrogen side is going to be at 30 bars, and on the oxygen side is virtually going to be at the ambient pressure or slight pressure, but we'll go into that shortly. Yep, and we'll look at this part here now. So we've got the plate heat exchanger. So of course the process water that comes out of the electrolyzer stack will go into the plate heat exchanger, and the plate heat exchanger is, of course, there's going to be a stream in which is going to be processed water, stream out is also going to be processed water, but then we'll have a cooling medium going in and a cooling medium coming out. And one of the reasons that we need the plate heat exchangers and we can't just put the water straight into the air blast cooler is one is that it's going to freeze because this must be, of course, outside. How cold does it get in Germany? Does it get -10, -20 in the winter? Yeah, it's going to freeze. So we want this to be filled with cooling medium. copper air blast cooler is more efficient but will corrode near seawater. So of course this is a copper air blast cooler. You must not have this sort of 1 or 2 kilometers near the sea because it will corrode. It won't last for a very long time. What you can use in that case, if you're very close to seawater, is stainless steel. And the trouble with stainless steel is that it's not as efficient with conducting heat, so therefore you are going to need a larger air blast cooler because, and of course that is going to mean an increase in capex and an increase in footprint. And the second reason that you need the plate heat exchanger, so the first one was freezing. The second reason we need the plate heat exchanger is because if we were to pass processed water through the air blast cooler, we could not use copper, or we could, but basically that would be terrible for the stack long term, and also it would corrode. Because we cannot use an inhibitor. We would have to use stainless steel for the air blast cooler, which means it would have to be larger, again, bigger footprint, bigger capex. So what we can do with the plate heat exchanger is we can put in an antifreeze and we can put in an inhibitor. So the inhibitor will mean that we can use copper and it's not going to corrode. Let's look at, and this kind of comes under a little bit of innovation, but well, okay, it has been around for a long time, but it's kind of innovative. But we'll go into some more innovation later, don't you worry. So we've got the traditional air blast cooler, where, does it go up to 35 in Cologne? It probably does, I suspect, yeah, 35, maybe even sometimes 38, I suspect. It doesn't go that, it doesn't, in England we don't get 35 or 38 very often, but 35, you add an extra 3 degrees and your cooling medium is going to be 38 degrees Celsius. So if the temperature outside is 35 degrees Celsius, then you are able to use this to cool down your medium down to 38 degrees Celsius. If you don't know what a medium is, it's a witch doctor, witchcraft. That's what the medium means. And has anybody gone through a mist gate before? A couple of people, okay. In England, we don't have mist gates. We don't need mist gates in England. England is a big, giant mist gate itself. But I think this picture is in Budapest, and they definitely need mist gates there in the summer. And we've got mist gates. The way mist gates work is they take water, and the water doesn't have to be cool. The water can even be like 35, relatively warm water. It could be even this bott. What happens is it's not the cool water that cools you down. What actually cools you down is that when you put this mist into the air, that water is going to very quickly evaporate, and due to the latency of evaporation, that air mass is going to be cool, and when you walk into that, that just feels great because you're walking through essentially pretty cool air. So what happens, the way we can utilize this is we can utilize a water sprinkler system to pre-cool the inlet air to the grills. So essentially, we are putting the air blast cooler into a mist gate, and it can enjoy the mist gate. And even if the dry bulb, so even if the outside temperature is 35 degrees Celsius, we can pre-cool the air going into it down to 23 degrees Celsius. Add 3, and we'll end up with 26 degrees Celsius. Fantastic. So we can use that at great for hot climates where water is inexpensive. So I was working on a project which was going to take place in Mauritania. It's a 250 megawatt solar hydrogen project which will be built in Mauritania in the next 3 or 4 years. And we were looking at desalinating water and using it to cool, using it as an adiabatic heater. You're using that water for our adiabatic heater. And of course, this is the difference between the two. And then again, of course, we're talking about this area. So next up, we're going to talk about the temperature swing desiccant dryer. So the next slide, this is what the next slide looks like. So just so I don't want you to get confused. The deoxidizer is not going to be on the next slide. On the next slide, we will only have anything downstream of the deoxidizer. So the deoxidizer is essentially a vessel with a little bit of heating, because we don't want it cool. basically, because we do not want any condensation to take place in here. If the catalyst in here, and these tiny beads, I'm not sure if you've seen them, these catalysts, these palladium-based catalysts, and if there's any water in here, then essentially it will turn into sludge. We don't want that. But the next slides are going to be just there. So this is how the temperature swing desiccant dryers work. We have desiccant material in here, desiccant material in here. At the moment, B is redundant, so B is not being used at the moment. And A on the left-hand side here is being used. And I'll show you how it works. So the gas comes in, it will go through a cooler, and the cooler is going to cool down this gas to approximately 10 or 15 degrees Celsius, sometimes even 20. It will cool it down. And just so you know, the gas going in is going to be around 50 degrees Celsius, 100% saturated, or very close to 100% saturation level. And the gas goes into the cooler will cool it down to, like I said, 15 or 20 degrees Celsius. And the gas will, so there'll be condensation in here. And the automatic drain will take care of the condensation water. Will go out. And the gas will then go into this, I keep on tripping on these. The hydrogen is still saturated, but it's only at, the dew point is about 10 or 15 degrees Celsius, and the gas will go into this vessel, and when this vessel is relatively cool, i.e. 10 or 15 degrees Celsius, the desiccant will take in all the water. So if you imagine if you have a phone that's not waterproof, you drop it into water, your grandmother will tell you that you should put it into rice, because the rice is going to act like a desiccant, it will dry your phone out. That's exactly how this will work. So we have the desiccant, and silica gel desiccant looks like peas, or even smaller than peas. And one of those beads will actually have around the surface area of around 25 square centimeters. So one of those tiny beads will have a surface area of about 25 square centimeters, which is obviously a huge surface area. And then it's going to remove all of that moisture, and then what you have going out is going to be very pure hydrogen gas, down to the parts per million level. And you can even use these kinds of dryers to get you down to the parts per billion level. However, that is just not necessary. Parts per million, 2 or 3 parts per million is just fine. So you might think, what will happen when we keep on using this column? Well, eventually this column is going to be fully saturated, and it cannot suck in any more water. It cannot take in any more water. Well, what we must do is, we've got the gas inlet here. Part of that gas inlet is going to go through a heater, and this heater is going to heat your gas up to, I don't know, 200 degrees Celsius or 250 degrees Celsius. Let's say 180 to 200 degrees Celsius. It does depend on system by system. I've worked with various different systems, so let's just say 200 degrees Celsius. This gas will be heated up to 200 degrees Celsius. Well, you've just lowered the relative humidity because you've heated up the gas. Well, you pass that really hot gas through column A, and the way you can think of this desiccant is that if you pass hot gas, it will take in the moisture. Essentially, the desiccant will release the moisture, and if you pass cold gas through it, then the desiccant will suck in the moisture. And then you've got the gas going back into the cooler. The cooler is going to cool your gas down to about 15 or 20 degrees, 10 or 15 or 20 degrees Celsius. Again, it's dependent by which system you're talking about. And the bypass gas is going to mix in the cooler. And again, the exact same thing. There'll be condensation taking place here. The automatic drain will take care of the condensation water. And we are going to pass the gas into column B, and it will go through column B up to the top, and the gas is going to again just be very dry, very highly pure gas, and then the gas will go and will go and be sent to our customers. So we need obviously the cooling for this cooler, and the cooling is going to to be provided by a refrigerant chiller typically. Some research has actually gone in to basically get rid of this cooler and use a different type of a cooler. So, refrigerant coolers consume a lot of power. They are very high capex. They have very complicated maintenance schedules, and they consume a lot of electricity. It's just like it's really hot in here. We don't have the air conditioning, and I can tell. Yeah, it's very, very hot in here, by the way. I think a lot of people would agree with that, actually. Maybe if you could turn the temperature down, that would be great. But it would be okay to get the temperature down. Yeah, thank you, mate. Cheers. This is essentially an air conditioner. And if you have air conditioning in your house, you know that if you turn on the air conditioning, you will just, I tell my child not to turn on the air conditioning and my wife not to turn on the air conditioning because it's going to cost me a bloody fortune. So it's exactly the same thing here. We are wanting to replace this with adiabatic coolers, basically. And the way you can do that is you can replace this by an adiabatic cooler, but you have to also modify the dryer. So there's actually quite a lot of research going into that to reduce the cost there. And of course, we've been talking about this part here.